Welcome to this test talk 2021. I am François Marcotte, a subject matter expert working in Montreal, Canada. I've been working for Exfo now since 2003, so 18 years. So I'm supporting basically testing for wireline and mobile type transmission. And today I will talk about timing and synchronization in 5G. So the table of contents, so very simple. First point will be explanation on time error in 5G system. And second, I will show you a live demo of a time error measurements with a grandmaster. So understanding time error. So let's go with types of timing. So absolute timing, so time of day, of course, place and zone, of course. And then you have UTC, used by operators around the world, and many standard are using UTC, so coordinate universal time. Frequency timing for synchronization. So in this type of synchronization, you are basically you need to have the same frequency, meaning that when a bit is moving, let's say Montreal, and if it's on the same network, it's moved at the same time in Dublin. So the same frequency. So the period of time between the two pulses is the same. It's very important to synchronize transmitter and receiver. And that was, of course, used in SONET and OTN. Phase timing. Phase timing is, of course, you need to make sure that the clock pulse is exactly the same. So when you compare a reference clock to the measured clock, you want to make sure they are aligned in phase. So alignment, basically. So that is very important, of course, for LTE Advanced, 5G, and TDD. And 5G beamforming. As you know, beamforming is a process in 5G where they redirect, they take multiple antennas and they direct energy to the mobile device. So they get an optimal air time, we say. Why synchronization? Audio and voice, obviously. Reduce noise, clicks, make sure latency is under control. You don't have too many drop calls. Your video is not corrupted with pixels and lines and freezing. Wireless networks, of course, seamless handover. You want to move from 4G to 5G. Synchronization is quite key. Because you're going to have, of course, in your network, 5G and 4G system working together, obviously. So when you're driving around with your phone, you want to make sure there's no clicks, no more drops, let's say. So carrier aggregation, dual connectivities, and of course, accuracy per location. And somebody's calling me. Application impacted service, of course. So location service, industrial automation. For example, you are a farming enterprise, a large one, right? Many cows. And so you need to synchronize your water. You need to synchronize supplies of grains. You need to make sure milk is properly filtered, etc. So all this needs a very high level of synchronization. And IoT, of course, Internet of Things. You have smart cities. You want to redirect traffic when in a zone is congested. So if your synchronization is not good, you may miss, of course, some information about the traffic going on. So network monitoring is quite important. And synchronization is the key, if you ask me. So moving the network around, upgrading from 4G to 5G needs synchronization. So the GNSS was mainly used in 4G, and that was for North America, as I know. In the rest of the world, they may have used, of course, direct rubidium test synchronization, which is very expensive, by the way. And then moving forward with 5G, then introduction of PTP, introduction of SYNCI. Today, I'll focus on PTP, of course, which is the very popular synchronization method defined by G8275.1 and 0.2. I will correct that before I send that to everybody. So what is PTP 1588? It's a standard, right, defined by IEEE. It's for time precision, and the time precision is introduced in a Ethernet packet. So there's a place in the Ethernet packet called PTP message, and that PTP message carries the synchronous or the synchronization information, right, like the timestamp that was required for phase and shift. So uh, it provides frequency, phase, and time of day, very important. It's distributed along the network. The prime reference clock is GNSS source. And we are, of course, assuming in this type of technology, PTP 1588, that the downlink and uplink delays are the same. However, I saw onto a customer that there was a variation between the downlink from the grandmaster to the bundary clock, and from the bundary clock to the grandmaster, it was taking a different VLAN and circuitry. That can be a problem because of delays that can be introduced and correction that the bundary clock should be doing. So if you look at what are the different message and information that the bundary clock will be doing is, of course, it knows the grandmaster time when it received the sync message. So it knows the slave time when it received that sync message, so time T1. It knows, of course, the time it sends the delay request, so time T2. It knows when the grandmaster receives the time also, because the grandmaster will provide this information in the delay response. So it knows the T3 time. It knows the processing time of the grandmaster because it knows T4 as well. And then it received the delay response with all this information in T5. So then you can do, of course, measurement and then do T3 minus T0. So it gives you the round trip time, including processing time of the boundary clock. Then you do T2 minus T1. This is the processing time itself of at the boundary clock. And then you can measure the cable delay with some method and matrix, simple calculation. Then something that is not showing here is the packet delay variation, PDV. That because T1 and T2 is repeating, because you're getting a lot of sync message, you're sending a lot of delay requests, you're getting a lot of delay response. And this is over time, right? It's not 1 and 4 and thank you very much. No. There's message per second that you should respect, 16 message per second, 32 message per second, etc. So this is something you have to set in the grandmaster in boundary clock. And then you can compare your T2 minus T1 over time. And you can see that packet delay variation happening, or this processing time and these type of variation. And then you have to be by the standard ITUT. You need to make sure you are below 200 nanoseconds for PDV, for example. So what are the metrics for time errors? So how do you measure it? That's simple. So here you have the reference clock. This is, of course, a reference you're taking. And in our case, we will be taking it from the GNSS. So we have a built-in GNSS receiver in our test equipment with very high precision. So it's quite cool. And then you are also measuring with the test set the clock at that boundary clock device. And then you compare both. And then you get over time that time error. And you can see if it deviates too much. And you can then measure different matrix. I'll get to that in 2 slides. So measurement consideration, that's exactly what I was saying. We have inside that FTBX 88260 a GNSS receiver, a sync module. So you just connect an antenna to it, making sure there's no, of course, too much, let's say a thunderstorm outside or cloud, because it will take more time to lock. You will lock eventually, but you may lose precision. I'll get to that after in the demo. Then you compare it to the measurement. So the measurements, you have 2 choices. You can decide to take it from the Ethernet signal itself. So you do exactly what the T boundary clock is doing. So you recover that synchronization out of the PTP. So you're doing the same process, and then you compare it with the reference clock. That's cool because you're doing exactly what this boundary clock should be doing. Or simply you get the 1 PPS out of this device. And if this device is capable to give you, of course, the 1 PPS, then you can use that as well. Now, you need to know a few things, and I'll explain that during the demo, in fact. So time error matrix, if you compare them, you can then get, of course, different matrix. So what are the matrix? Constant time error. So that's the one you can see right here. And this vary over time. As you can see, it's the mean level of the time error function over time, right? So if you have, of course, higher time error or maximum time error, then obviously this constant time error will then increase. Then you have the dynamic time error, which is right here and right there and right here, in fact, of course, as well. So this is for an observation time, this is the amplitude peak to peak that you're getting, right? And then you have the maximum time error, which is the largest difference between the UTC and the maximum you're getting. It can be a positive or a negative. Huh? So meaning your clock can be in advance or late. That's why we see here negative values and positive values. GNSS is, of course, as you know, you have multiple satellite in space where you can lock on. That's cool. And then you have accuracy. In here, I'm talking about accuracy of 3 feet and 4 nanosecond. In fact, with GNSS, you can get down to 1 meter. And then, around 5 nanoseconds. So it's basically the same. 3 feet is around 1 meter if you do the calculation. Synchronization now requirements. So of course, there's boundary clock qualification that you have to do. And then time error measurements. You have to decide, are you doing it on Ethernet or 1 PPS or both? So that's in the lab. I would recommend you do both so you can compare if your boundary clock device that you're building is correct and in meeting the time error. And then you can compare after that with the 1 PPS, which is just slightly higher precision, but then you can see the difference. Then the limits defined by ITUT 8273, you can see them here. You have different boundary clock class, A, B, C, D. C is a little bit crazy, if you ask me. It's tight. You should say tight. That's proper word. But if you can get there eventually, that's quite very good. People right now are looking at class A, basically. So 100 nanosecond for maximum time error and 50 nanosecond for constant time error. And it's time for the demo. So we go for the demo. Here we go. When you start the test set, as you know, and if you are familiar with Expo, you have multiple test capabilities. Here we're gonna do, of course, the time error / wander. So that's pretty cool because you can do the wander also in that same test. So under test configurator, you need to make sure what is your input. Is it 1 PPS or Ethernet? In my case, in my setup, it is 10 gigi. So that's fine. So that's why I have a link up. The PTP is using the standard ITUT 8275.1. And you can see here 8275.2 is a possibility as well. And you need to make sure, of course, it's the correct domain. Be careful about that. And we are using the synchronization message of 16 messages per second and delay requests. You may want to try other level of message. I understand in your lab you want to try different ones. And then when you did set it up correctly, you can then use that and compare. Here you see here, there's already a threshold, a verdict for packet delay variation of 200 nanosecond. That's fine. And then you have the time error itself, where you decide what is the constant error. Here, I'll put 100 second. That's sufficient. This is the period to measure dynamic time error. And then some threshold you can set for your, of course, your tests. You can decide on these value, and then you can be very strict, like class C if you want, or be very, loose, like I am right now. and then you start your test. So the test goes into, but before I start the test, that's right, I'm forgetting that very important step, is synchronization with GNSS. So you have to go under the system and then look if you are, of course, locked to the GNSS. And when you get a ready and lock, there's a jamming. Jamming means you're getting interference. So when there's a clear day, you will not have as many warning, but that doesn't matter. You are ready to go, your luck. That's the important factor. And of course, here it's the desired accuracy. You can decide very high is, like I said, 1 meter accuracy on the satellite. So that's quite good. But if you are having, let's say, cloudy day or rainy day, and you don't think you're gonna have as higher accuracy, then you can reduce it to high, medium, and low. Earlier, Javier had a question about that. He said, "What is the, what is the guideline?" And I realize we will provide that to customers. That very high means, when you are here observing, we're going to provide actually a template that helps you to define what is very high, medium, and low. There is also on the test set, a question mark that helps you with these different things. And we are giving you some indication, what is cable delay, what is the, status, etc. So there's always information, but about the accuracy, we will add that as well. So now when you're making sure everything is fine, you're going back and now you really start your test. And now you're measuring your time errors. So the time errors, so people can go outside. Of course, you need to allow 15 minutes to make sure you have a lock on the antenna and have holdover. Okay, so when you have holdover, everything is fine. Then you can measure your time error. And now, how long should you measure? That's a good question. We used to do wonder tests for weeks. Now, for time error, it's not as necessary to be very long. So we see out there people doing 45 minutes to an hour and a half time error measurements, and plus the GNSS lock. So that gives you an idea about how long this test would last. And then you have enough time also to get your dynamic time error and your maximum one and constant time error. I did put 100 seconds, so that's almost 2 minutes. So we'll wait for that to get some values. I'll come back to this. Then you have your PTP statistics. That's quite interesting to see, because you see here, you remember your forward. Forward is you're sending the delay requests, and reverse is from the grandmaster to you. So you can see here the deviation, right? And the round trip delay. So you can see here we have 2.5 macrosecond round trip delay. That's quite good. And you see here how many on the message information. That's something you need to keep track. And if you're not losing any message or because of packet loss and stuff like that. We have a failure here. You see on top. You can go on the logger and see, okay, what happened? Oh, you see the maximum constant time error is below 100 nanosecond. Maybe I was too strict about that. So I can go into the back to the summary. Sorry, clicking here all over the place. And you see here the maximum was a little bit too low, right? Minus 132. So the 100 nanosecond was crossed, and then I have an issue. So something to check on my, again, I'll talk about troubleshooting after, but this is something you need to check. So segmentation has to be done. Under alarm and errors, this is Ethernet alarm and errors, and of course, PTP. So you can see, do you have sync loss? No. You have announcement loss? No. Or a domain problem. If you have a domain problem, then obviously you won't have sync. But that's the normal things. Perfect. So that's the setup. I have a grandmaster, an Ethernet link, and then I have a device which is giving me 1 PPS if I want, or Ethernet. I'm connected right now to the Ethernet link, which is, of course, the purpose of this demonstration. And then I'm locked to a GNSS antenna, as you saw. Now, here you have the test set with the GNSS antenna, and you have a trouble. So it can be in a lab, it can be in the field. You're measuring here your time error, and you have, like I do right now, having a problem. So my constant time error is too high. Okay, I'm too late. In my case, I was minus 132. So I'm late. Okay, so then I can move to the other element on the Ethernet link. So even though this is not, let's say, a device that is capable to give me a clock, no problem, because Ethernet is carrying the PTP information. So then I can read it exactly like I said, like a bundary clock system. So then I can then measure here my time error at this position. It's bad. I have the same problem here. Okay, so I go here. In between those two elements can be two switch. And then, okay, I'm measuring that everything is fine. So then my problem may be this device right here. So then I can, if there's no clock there, I can replace it with my device and troubleshoot, make sure this device is not adding too much delay and too much packet delay or jitter. If it's adding too much jitter, then you have an issue, by the way. Okay, so that's troubleshooting, of course, that you can do with the system. Any questions at this stage?
So we are here troubleshooting. We are proposing a GNSS solution for testing, but there is a tendency to believe in the market that the right way or the accurate way to measure is with rubidium atomic clocks. What do you think about that?
But first, it's expensive using rubidium clock all the time. But that's a good question. So just to again summarize, you want to know if GNSS way versus rubidium, which one is the best, right? It's not practical to use rubidium. First of all, because of oldover stability concern. You know, as you saw with the GNSS, it takes 15 minutes to lock on a antenna on a satellite, or actually many satellite, to get the nice accuracy of below 40 nanosecond and even 5 nanosecond. So that's very interesting. Now, of course, the rubidium can give you a more accuracy, a little bit more accuracy, like 2-3 nanosecond accuracy, but that is where if you go in class C. Now, class A, class B, you're fine with GNSS. It's faster. So it's, of course, short term for stability. So there's a powerful oldover stability as well for long term, right? So when you have oldover, you can, lose the communication with the satellite and then still use the test set. That's pretty cool. Also, it's lower power because rubidium is taking power. And also, you need to have an engineer because, rubidium clock mechanism usually requires engineers, so they have to be involved. So it increases, the turn up or or troubleshooting cost. And of course, all in all, everybody is now using GNSS. And if you look in labs, what has been done into different manufacturing equipment manufacturers, they are using GNSS as a reference.
There is a question in the chat in the same context.
Okay, can you?
Marcin is asking if it is possible to do simultaneous measurements of 1 PPS and 10 gig port.
At the same time?
Yeah.
It's possible. Everything is possible, but in one blade X4 test module, it's either 10 gig measurements or 1 PPS. Now, if you want to do both together at the same time, you can put a second blade in the same chassis, and then you can compare both together. So yes, in a setup where you want to compare the 1 PPS with the 10 gigi, that's fine. And in the same screen, you can actually have two. You can see the 10 gig or the Ethernet deviation, or let's say time error, versus the 1 PPS time error, and then it's possible to do both at the same time, but it's a little bit of a different configuration.
Okay, so he's adding in the same direction. I think you already answered, but as well as SYNC and PTP simultaneously, right?
Yes, yes, yes. So good point. Let me go to the demo, because sometimes it's better to see, we believe what we see. So I have here, I'll stop the test. And it's doing nice reports with graphics, by the way. And you can see here you have SYNC. You have also independent 1588 PTP if you want to measure, let's say, phase deviation and stuff like that. And CIPRI. So what is happening in the lab right now, I saw some people are doing, I know I'm going over time a little bit, and I'm happy you're asking this question, and I will answer before I stop the recording. So people are testing CIPRI and eCIPRI. So they have to validate that. After that, if they have SYNC, they need to validate, of course, SYNC. So they start SYNC. And then they do the time error. Now, if you want to do both together, it's a configuration thing. You can have a device with a few test module where you can run multiple of these tests together and have the end results. If you are in a manufacturing arena or lab, you can send script and automation. So you do SYNC first, time error with this module, and then the other one is tracking CIPRI bit errors. And I hope I'm answering clearly the question. If you have any other question, I invite you to send it to us. We will be more than happy to answer. Thank you very much for your time.